Hi there, and welcome back once again to this course in ENSC111. We're in the topic about the thermodynamic properties, and right now we are going to discuss the temperature. So, temperature is a property that is elementarily defined as the hotness or coldness of a body. So, we say that if a body is hot, then somehow we know that it has a higher temperature, and when the body is cold, then we feel that, or we know, or intuitively we know that the temperature is low. But actually, we need a deeper description of this temperature property. So, a much deeper definition or description is that we take a look at the microscopic view of the molecules or the movements or activities of the molecules. So right here in the figure, we have a container of, let's say, a water inside the container. So it's just exposed at some ambient conditions, so without being heated up here. Then another one is a container with this water, but since it's being heated up, then therefore, let's say it has a, um, let's say it has reached a condition wherein it's boiling. So if we take a look at this microscopic view for the water in this situation, we just see that the molecules, they have emotion, or they are moving, but it is relatively slower or less energetic as compared to the ones here. Let's say if it's being heated up, then we see that the molecules here are really energetic as compared to the other one. So therefore, we say that the temperature is actually related to the kinetic energies of the molecules. So at lower temperature, that means the molecules have lower energies, and for higher temperature, then that means the molecules are more energetics. So to quantify the temperature, what was used was a liquid, because when a liquid, or actually any substance, or most of the substance that's heated up, it expands. So they use liquid right here. So here's a, let's say, a glass thermometer. Then there's a liquid here. So it could be, let's say, mercury, or maybe other possible liquid with a better expansion characteristics. So once this liquid is heated up, then it's going to expand. So once it expands, then since we have a constant area here, so that means there's gonna be expansion along the length or along the height, and that expansion of the liquid corresponds to some measurements in the temperature. So let's say here is the zero value, or 0 degrees C, and then right here we have a 100 degrees C. So anywhere in between, there's gonna be calibrations or measurements made. So the set of fixed points, let's say the 0 degrees C and the 100 degrees C, as based on the freezing and boiling point of the water. So freezing of water is set to be at 0 degrees C, and then the boiling of water is set to be at 100 degrees C. But it has to be taken note that the freezing and boiling points of water, that is 0 and 100, corresponds to 1 atmosphere, or atmospheric conditions at sea level conditions. So that means that if the location is away, or the height from the sea level condition is, let's say, it is higher, that means that there's going to be a change in the values of the boiling or freezing point. So let's say on the mountain locations, so it has lesser pressure or lower pressure as compared to the sea level conditions. So that means you would achieve a lower value for the boiling point. So just to have to prevent some discrepancies, and also it was tempted that instead of using a liquid thermometer, then why not use a gas instead? So when using the gas, it's actually the same, that when the gas is heated up here, so once this is heated up, then it's going to expand. And the opposite of expansion is contraction. So that means, let's say, by the way, there is this liquid mercury here, so that the gas will not escape the tube. So that means if this if this expands, then that means it will just push this level of mercury on this side, and of course, if it's going to push it downward, then that means the other side will have to go upward. So the difference in the heights corresponds to some temperature readings. So right here, let's say the condition here is colder because it is, let's say we have ice, cube ice here. So that means gas will contract. So if it will contract, then that means from this initial point it will contract. So that means the height of the liquid here will rise up on the left side, and because this will rise up, then the other side will have to go down to maintain the constant volume, and then there's going to be a temperature difference for the reading. So on the other hand, if this gas is exposed to some hot conditions, then the gas will expand, and then from the initial level of the liquid mercury, and it will go down on the left side, and then it on the right side it will go up. So they have observed that if they plot this product of P times V, so the pressure times the volume against this temperature, then they see that, let's say when using gas A, then they have found out that there is a linear relationship. So if we plot from 0 to 100, then they see that it's a linear relationship when using some, let's say some composition of gas, and let's just call it A. Then when using gas B, of course there's going to be difference in terms of the points, but the relationship again is still linear. So when they superimpose this and then try to extrapolate, to extend this, so they found out that there's this point, or it meets or it intersects with this point right here, and that point corresponds to a value of negative 273.15 degrees C, and that is now the what we call the absolute zero temperature. So so it's not just based on some freezing point of substances, but rather it's a more absolute scale, which is the absolute zero temperature. So that is negative 273.15 degrees Celsius. So instead of using Celsius here, so it's like transposing. So instead of 0 here, so this will be the new 0 value, and if in that case, then the unit of the temperature is now in terms of Kelvin for the SI units, or Rankine for the English units. Okay, so now the relationships between the absolute and the relative temperatures. And when I say relative, those are the temperatures at degrees C or degrees F. So here they are. So temperature for Rankine is simply the Fahrenheit value plus 460. And for Kelvin, so Kelvin is just equal to the temperature at Celsius plus 273. And also one thing to take note is that sometimes we'll be we will encounter the change in temperature. So like for example, in the equation later on for the sensible heat, so Q is equal to mCp delta T. So here's the how much heat is required to raise a mass of water from some temperature values. So there's going to be a temperature range, let's say from 30 to 60 degrees. So if there's going to be delta, that means 60 minus 30. So we'll be dealing with this delta temperature. So if we are dealing with delta temperature, then the degrees Celsius is just equal to the Kelvin. Okay, and then for the Fahrenheit, degrees F is just equal to the runtime. So that's just the, because we just add up here 460. So they're just actually the same thing. So you can try, so maybe 60 plus 273 and then minus what's this, minus 30. Okay, 30 plus 273. So the difference is just, I think they're just gonna be the same. So you add 273, 273, so it's gonna be minus, so it's just 60 minus 30. So what's left is just 30 degrees. So again, if you happen to come across with this delta temperature, the degree C is just equal to the K. Okay, so we have here a sample problem. It says a system has a temperature of 25 degrees C, and we are asked to determine the value of its temperature in Kelvin and runtime. Okay, so what we know so far is the conversion of the Celsius to Kelvin, which is just, if we write it directly, so let's just say solution. So converting the degrees C to Kelvin. So that means Kelvin is just simply C plus 273. And the value here is 25 plus 273. This is, I think, 298. So 225 plus 273, 298. So 298 Kelvin. Okay, next for Kelvin to runtime, if we know the value, then that's fine. But let's say in my case, what I know is just the Celsius and the Fahrenheit, and then Fahrenheit to runtime. So I'll first going to convert this Celsius to Fahrenheit. So convert Celsius to Fahrenheit first. So what I know is degrees F, or the Fahrenheit temperature, is just equal to 1.8 C plus 32. So 1.8 times 25 plus 32. This is equal to, so 1.8 times 25 plus 32. This is 77 degrees F. And now I can now convert this degrees F to runtime. So runtime is just degrees F plus 460. So 77 plus 460. This is 537 R. 537 R. Okay, so next property that we'll discuss is the energy. The energy is basically defined as the, or something, or is a property that's that has the capability to produce an effect. So let's write here something or property that has something that has to do something that has to do with or capability of producing, or capability of producing an effect. Producing an effect. Right, so that's the definition that we will use. So it's not the capacity to do work, but rather I think it's more precise if we use this capability to produce an effect. So it's subdivided into three. And when I say property, that means it is being possessed by the system. So first one is the potential energy, then next the kinetic, and then last is the internal energy. So these are just the three energies that we'll consider in our analysis. When I say potential energy, it is the energy possessed by the substance or the systems by virtue of its position in the gravitational field. Because there's this gravitational field and the substance is in that field, then therefore there is this potential energy. So whether that is in motion or not in motion, it is, or it has this position. I mean, because it is in this field, therefore it has this potential energy. Okay, next one is the kinetic energy. Kinetic energy is the energy that is possessed by the substance or the system by virtue of its motion. Well, because of its motion, it's moving, it has some velocity, then there is this energy associated with that motion, and that is what we call the kinetic energy. Okay, and last one is the internal energy. And this internal energy is just simply because the substance is, by itself, it has this energy with without respect to the gravitational field or its motion. So just being by itself, it has this energy, and that is the internal energy. So this is defined. This internal energy is actually defined as the sum of all the microscopic forms of energy of a system. Okay, so actually, what we that we'll encounter later on is not just the potential energy, but rather the change in the energies. So that's why we use this equation delta. By the way, here, so for the potential energy, this is mgh. So this is a unit of energy because m is in kilograms, let's say kilograms, and then g is meter per second squared, and then h is a unit of length. So we have newton meter. This is joule. This one, the kinetic energy is ke. So I should have write pe here. This is 1/2 mv squared. So 1/2 unit of m is kilograms. Okay, so let's not write this anymore. Kilograms times meter per second. That's the unit of velocity squared. So kilogram meter per second squared times the meter. This is just equal to the unit of energy, which is joule. Newton meter. Okay, so as I was saying, what we will encounter later on is not the energy at one point, but rather a change in energy. So we we are going to express the equation like this. So delta P, that means this a change in the potential energy, let's say from point 1 to point 2, or condition 1 to condition 2. So mg times the delta H. So the variable here is the height. So if there's a change in height, then we say that there is a change in potential energy. But if the height difference is just small enough, then we can neglect it. Like for example, we have this tube, then we have this flowing water here. So if the height here is, let's say this is 0.2, this is 0.1. So since we have a difference in the height, so if it is negligible, then we can assume that there is no change in potential energy. So that depends upon the idealization. Now for the kinetic energy, then it's just simply 1/2 m times delta v squared. So let's say from rest, then it goes into motion, or let's say at first it's traveling at, let's say, 1 meter per second, and then after some time it accelerated to let's say 2 meters per second. So there is a change in the change in the velocity, so therefore there is a change in the kinetic energy. Now the change in internal is actually without respect to the potential or kinetic, because let's say we have this system here, or our substance is the water. So it didn't change the height, let's say at condition 1, it's just there at the table, let's say. So here is a condition 1, or the state 1. So it's after some time, or let's say after being heated up, then of course the condition is that it's going to boil or increase the temperature. So it still didn't change the height, and also let's say it is at rest. So let's say at point 1 it is at rest, it's not in motion, and at point 2 it's also not in motion. So is there a change in the energy of the system? Then the answer there is yes, but the change is in terms of the internal energy. So it's not just the potential kinetic, but also the internal energy. Right, so the temperature increases, so that means there must be some energy that go into, or that went into the system. So even though it's not moving, or it didn't change the height. Okay, so now let's move on to the next property, which is the enthalpy. So enthalpy is another property, but actually it's a compound property. So what it means is it is, or it consists of many other properties. So this is actually a frequent to see the sum of u and then the plus the product of this p v. So in terms of mathematical terms, I mean this is h, that's the enthalpy, and then u internal energy, and then p is pressure, and v is the volume, right? So u plus pv. So this is going to be common to see later on, especially when we are going to deal or do the analysis for open systems. So it's not just the u, but rather the plus the flow work, or something like the moving boundary works. So um, so sometimes this is referred to as, I mean, the h. It is a measure of the or referred to as the heat content. But since heat is related to some, I mean, depending upon the type of systems and the interaction, so it could be heat or it could be maybe work. So anyway, this is a compound property, and just to have some detailed discussion about this PV. So we have here the PV, but the PV was shown to be the energy. It says here the energy necessary to force a given mass of fluid across a given boundary of a system. So that means, let's say we have this mass in motion. Let's say here's our boundary. So how much force or how much energy is required to force this unit mass across a given boundary of a system? So if there's a force, I mean, of course, it's going to be related to the energy. So that is somehow related to this term, pressure times volume. So it's only an energy when we're dealing with fluid in motion. But if the fluid is at rest, then take note that the PV term is or cannot represent an energy being transmitted, since no energy is being transmitted. Okay, so again, we are still, I mean, sometimes we are interested in the change in the enthalpy. So that means at any point in the system, let's say at this entry point, so we have an enthalpy there, we have a, let's say a mass here, or a volume, a specific volume, or whatever properties, or temperature or pressure. So here we also have, since it's a point, then there's going to be a reading for the enthalpy, temperature, pressure, and many other properties. Okay, so the last one is the entropy. So entropy is another property, and we said in our first topic, I guess, that the entropy is something like the dissipation of energy. So because we cannot actually utilize the energy input, I mean all of the energy input. So let's say again, here's our system. If we input 100 kilojoules, then we cannot get a 100 here. We can only get something less, because some of the energies is actually dissipated. Let's say here we only have 80, but then the losses to sum up into 100, then let's say this is just 20 kilojoules. So there's actually losses in the system. So that's why we said that the entropy is the dissipation of the energy. But then if you think about the opposite view, so we can view this entropy also as how much energy can just be recovered. So therefore it refers to the availability of the energy. But technically it is a measure of the irreversibility of a process. So that means because some process cannot be really reversed, then that means there's going to be, I mean, that is the reason why we have this dissipation of energy, because we cannot reverse the process. So in detail, when you say reversible process, it is a process that once having taken place, then let's say we reverse it back, then in doing so it leaves no net change in the system and in the surroundings. So that let's say, for example, we have here just a let's say here, let's say we have a block here that rests on some surface, and then here's our position 1, here's our position 2. So let's say we move this block from point 1 to point 2. So when we move it back, then in order to reverse it, then it just means that we have to push this back again to point 1. So here we apply the same force, so then it goes back to this point 1 position. However, it's not reversible because it says here, I mean, the description or the criteria for a reversible process is that it must leave no change in the system and no net change of energy in the system and in the surroundings. So it must go back to its original state. So the reason why it is not reversible is because when you move this, then there's gonna be friction here. So that means the temperature of the block will increase. So if we push it back again, then of course the friction still appears, so therefore the temperature will rise. So technically this is not reversible because the temperature um, of this condition is no longer the same as the temperature of that condition. So of course this is just hypothetical. I mean, we're just being technical, but in practice, of course, there are some like these situations. Of course, if the temperature rise is, let's say, negligible, then probably we can say that it is reversible. So to do that, I mean, in terms of um, in terms of just I mean, thinking about it, to make it reversible, then that means we just have to move this a little bit, um, a little bit of distance, so that the effect here, or the friction here, is it would be negligible. Okay, so that is, I think, what they call the quasi equilibrium process or something. Okay, so this is not actually reversible. And of course, some processes are obviously not reversible. So just like this, let's say we have this egg right here, and then once it's broken, then it's really hard to bring it back to its original state. So that is obviously an irreversible process. Okay, so again, when we say entropy, it is the measure of the irreversibility, but still it translates to the dissipation of energy. Okay, and since this is energy, then the unit will be still in, I think, kilojoules per some temperature. So let's check this later on. So kilojoules per, let's say, per Kelvin. So that's the unit of this entropy, and the symbol is letter S. Okay, so I think that's all for our topic number 2. So thank you for staying with me, and in the next video we will start our topic 3, which is the properties of a pure substance.